calculation. So that is mainly for the structural design. Yeah, what happens when you do a water hammer, in addition to the static head that you have some other pressures that you need to consider in the structural calculation of yours, you know. So what you do once you find the diameter of the penstock, for the structural analysis you determine the thickness of the pipe. Once you do your water hammer analysis, then you can do the thickness calculations, because you will need to know the pressures and everything else. But there is also another thing, that if there is a surge tank, there is also pressure from that into the penstock. So you can mention that, but pictures, because they are most important. Let me information, but the art you will not be able to learn totally in schools. You will learn that mainly from your projects, from your work experience, and from many other sort of works that you are doing from different people. Every time that you do a project, you learn a little bit more. Every time you do a different project, then it gives you a better idea. There is still the same energy calculations, the same formulas to calculate power, everything is the same. But when you do a project, that is not sufficient. You need to know other things, but then these other things, one part is to get information about different sites and different types of project, but the other part is that you also need to know and get information on other areas of engineering. Like the first thing that you do is to select the best site, because you want to build the dam so it is sound from a technical point of view and also feasible from other points of view, including or especially from economical point of view. So if you have a location where you want to select a dam for a high-head hydropower plant, if you go to see maybe between these two areas where is the best place, the first thing that you do is to look on the topographic maps. What do you look in the topographic maps? You look for a location where the valley where the water is flowing is narrow, but then in the back the valley is large, so you can create a big reservoir, right? This is not really the case for low-head plants, because in the low-head plants you are not really creating a reservoir. Maybe you do for a small volume, but the main thing in the low-level case is just that you built a small structure to impound the water a little bit higher. But then here, as I said, you look for somewhere where the valley is like narrow. That means when you build the dam, this dam, which may look like this, like a concrete dam or something, then you use a small amount of material to build the dam. And also from this information, if the valley is something like this, then you see there will be a big dam a very lengthy one, for the same amount of water to be stored. If we are talking about very mountainous areas with rocky cross sections, that may be good for a concrete dam. But if you find something that it is not really rocky, don't try to build a concrete dam. You should look for an earth dam, rock-filled dam, earth-filled dam, because normally it is a good idea that the type of material that you select for building the dam, this material matches with the natural material at the bottom of the banks of the river. Because in here, if you design a concrete dam, the water may seep through at the bottom, and then the concrete dam will not be worth anything. Underneath it will be eroded, and the whole concrete dam will collapse. And it will be difficult to sort of bond the concrete with the other natural material, which could be sand, clay, or something, but it's still sort of pervious material where some type of seepage still go through. So in here it would be better if you design an earth-filled dam like this, where you may use a clay core in between and then some other material here and there, and then if there is water seeping through, water can also seep through the dam itself. The only thing is it needs to be controlled. It has to be under control, and that is okay. But if this is like a concrete dam up to here, and then the water is going underneath it, that will be very dangerous for the stability of the concrete structure. While in this case, if this is a concrete dam and these are rocks, then they will design it in such a way so the bond between the concrete and rock is perfect and nothing happens. And if there are some cracks or anything here, they will grout it. The grouting means that you push some sort of fluid, cement and clay and other type of material with high pressure in these cracks to make sure that everything is blocked. They do similar thing also in earth dam as well, because if there is a little bit of seepage under the earth dam or through the earth dam, it's okay. But if there is a big seepage, then it is not good for the stability of this dam either. So there might be some grouting to be done on this on the ground here as well. So you see, it is really important to where you select the location of these dams. Now, in terms of hydroelectric power plant, whether the powerhouse will be here just within the dam or not, that's again a different story that you need to study to see where to build the powerhouse. But in the case of low-head hydropower plants, normally you are not looking for a big reservoir to store water, because in many cases they are run-off river schemes, which means that the water comes in the river, goes through the turbine, and passes, leaves. There is no big storage, maybe just a little bit. In here, as I said, the only thing we do is to raise the water level to some extent, or as much as you can. This is, let's say, the bank of the river, if this is a cross section like this. So in here, you are not really building a big dam. They are called weir or barrages or type of structures that lifts the water surface so you can create some height between here and the downstream water level, that you can use it in the turbine if the powerhouse is here to produce some electricity. So again, from site selection, this is also important, but on the other hand, if you see the plan, it is always good that you find a location that if you design the powerhouse, there is still room for the overflow. Okay? So you should select that type of cross sections where if you design the powerhouse, it is not going to cause any problem to the flow during the flooding time or when there is a higher water level. And then there is no sort of a standard that you do it this way or that way. It all depends on that specific location and on the specific project. And you can see these pictures that they all have different sort of orientation in terms of flow, in terms of the location of the powerhouse, and in terms of building everything else to make sure that we get the things done. Like in this case, this is the powerhouse, and in here, this is like a transformation station, and the other part is where the extra flow passes this section. And the rivers that where they also have navigation, the ships are going back and forth. They also include a navigation lock, because once you have this barrage across the river, if the river is navigable, from that time on, the river will not, the ships will not be able to pass this structure. So they will design a so-called a lock. This is something that you design a separate type of basin, just like if they need to know what size ships navigate through this river. And then they use that information to size the basin for the ships. Like there is a room like this. If there are smaller ships or canoes, what happens, this has two gates, one at the downstream side, one at the upstream side. The water level at the upstream side or the downstream side is low, and at the upstream side it is high. So what they do, they have some valves. When the ships comes from downstream, the water level in the river and in the lock is the same. So the ship can get in. Once the ship is in, they close the gate at the downstream side. Then they release a water valve from the upstream side to fill this basin up to the level of the water at the upstream side. When it is at that level, then they open the gate at the upstream side so the ship can flow and navigate further, go to upstream. And when the ship comes from upstream, they just do the reverse of this, which means that once the ship is in, they close the upstream gate, they close the valve, and they open another valve for the water to go downstream. So then in the basin, it gets down, down, down. Whenever it is the same level as the downstream water level, they open the gate so the ship can go downstream. So if this is such a river, then you have to include a navigation lock. But also from environmental point of view, you have to include a fish ladder. That means that there are sort of little steps and a small amount of water is flowing here. Okay, this is the water surface. And this is like the upstream side. This is the dam or whatever. So if a fish wants to go from downstream, they can go through this easily, no problem. But you have to provide that in your design, because otherwise, from an environmental point of view, this design will not be accepted. So there should be something for the fish to go up and down. Of course, the fish will also go through turbine, and sometimes it is dangerous for them. But they put some screen in there, and those screens may stop big fishes, but very small little fish can still go through, and it may be really dangerous. They get killed in the turbines, and that is not a good thing to do. So I really want you to see these drawings, and then when you have a project, if those projects are low head water power plants, these will help you to design your project from an artistic point of view, okay? Because this is important. This is nothing really a lot of mathematics or engineering, but once you select where you put the weir and where you put the powerhouse and everything, then you can do your calculations. That is to calculate the flow over the weir, and then how much flow is going over the or through the turbines. So if you so you need to find out, for example, this part of the section is for the overflow. This may be like, 3 different sections. You need to know how much are these lengths, and then you can use Weir formula to see if the amount of water going through this is correct or not. From a hydraulics point of view, we never went through Weir formulas or how they're derived and everything, but they're simple equation. This is equal to C times L times H to the 3/2. Weir, which is also the same for the spillway flow calculation. So this is like if I say L1, L2, L3, if these are equal, you can use the same formula, use 1L and then multiply it by 3, or you can use the total L, but you have to subtract these thicknesses. So, but most important thing is that the H that we are talking is actually here. So this elevation above it is V squared over 2G, and this is H, which is equal to depth plus V squared over 2G, which is what? Which is the energy, right? You remember? Or even a specific energy above this point. So if you have a flow going through this river, you need to do calculation a number of times. Number one, you have turbine flow plus weir flow, and this is your total flow. Okay? But what happens if the turbines are not working? And these may be, the maximum flow. If your design is not done properly, if something happens to the turbines and they are not working, then that amount of water needs to go over the weir as well. And if your weir is not designed for that flow, then there will be some problem. So what it means, for safety reasons, you design the weirs for the total flow, okay? Unless if there is another spillway somewhere else as an emergency type of spillway that the extra flow will go over that. And then how much is that total flow? We need to do some hydrological analysis and hydraulic analysis to find out when a maximum flow will be there and how much is that going to be. One day I mentioned briefly like Q100, Q50, Q200, that means 200 years or 100 years or whatever. In many countries they have a standard that for the barrages or weirs like this, you need to use, for example, 100-year flow. That means a flow that takes place or happens on average every 100 years. Okay? If you remember the hydrograph, it goes up and down and so on, sometimes really high. That means that these very high peaks occur rarely, but still maybe within the life of the project. So we need to design it for that, but at the same time we also have to take into account some sort of safety factor, which means that if the 100-year flow is, let's say, 500 cubic meter per second, maybe if there is a standard in the country, maybe they say that you need to take another 20% more to be on the safe side. Or if it is more important, the river, they may say use the Q500. That means the 500-year flow, because it all depends on where this site is located. If it is located somewhere near a big city, then everybody is more worried about it. And here, the flow may not do much at the downstream in terms of damages, but it may cause problems at the upstream side. In case of big dams, when a dam breaches, if there is important areas like cities downstream, then it may flood the whole city, right? But in this case, if the dam is, or the barrage is destroyed, nothing much may happen. But the water level upstream, it may cause some problem, because in low-head hydropower plants, normally we are dealing in much flatter areas. Therefore, a couple meters of water level at the upstream side, it may cause a lot of problem to residential areas or the cities, especially if they have the type of buildings that they also have cellars, like a couple of stories cellars, underground floors, and if something like this happens, then all those cellars will be flooded. And in places like Europe, if they get into this type of project, many people resist this type of project. They say that from an environmental and social point of view, this is not really a good project, we don't want to do it. So it is important to do your calculation and see where the water level is at the upstream side, but this calculation should be the maximum that you really need to consider because of other issues that will happen. The coefficient C in this formula, it depends on many things. It depends on how high is this, how high is the dam. Normally they show this as P. And also it depends on what sort of shapes you have here. And then on the shape of the bypass as well. This could be like a sharp crested weir, you know. Water is flowing just like this. Or it could be like a spillway. These types of spillways are designed on the basis of the equation for the flow. If there is an equation for the nape of the flow that if you do it, one equation for this surface, one equation for that surface, and they design it in such a way, the face of the concrete, that it matches the underneath equation, so there shouldn't be any problem. But on the other hand, they will also design some sort of aeration if this is a really large and big type of structure, to put some air underneath, because otherwise it may develop negative pressure which may cause cavitation. Cavitation, I think I mentioned one day, and when we go to High Head hydropower plant we will discuss it in more detail. But this is something that when there is a negative pressure, it means that there is a vacuum. And especially on concrete surfaces, if it is not designed properly, the concrete does not have enough strength, then it will sort of erode and scour that concrete surface, and then the whole dam will be like damaged. So the structural engineers with the hydraulic engineers need to make sure that when they design this type of spillway or chutes, they know how to deal with the cavitation, and also to provide some sort of aeration so they will not cause this cavitation. What they do, like for example, if they have this type of surface, they may put a pipe here with opening that air comes in, or they may cut a little section there, and then at the two sides this is connected with the air, which means that if any negative sort of vacuum takes place, that will be filled with air, and the negative pressure that may cause something will be diminished. So that way the concrete surface will not be damaged. What happened to? More simple way, if you see in here, the things is clearly mentioned where to put different types of powerhouses. Like, you know, in this case the powerhouse is located to this side. In this case it is located both sides. In this case it is located both sides, but at the same time there is a discharge channel at the back, which means that the water is going from this side to the turbine and then this way and going back to the river. So this is all something that you need to make decision. It means that if the land is available if the land is for this project, and if you can do whatever design, then if you are free to select whatever plan that you like, you should do an economical analysis to see which one is more feasible. But this is not only what you see from the land point of view, but this is also something to do with geotechnical information that we have. You know, whether this section is like a rocky type of geology, or this is clay, sandy, what type of material, and then from a stability point of view, from foundation point of view, and from many other points of view, which layout is the best. Now, this layout, if you see here, the powerhouse is located inside water, like this side is water, this side is water, but this one is more too close to dry land. Similarly, this and that. So maybe this has an advantage from another point of view, but access to that will cost some money, because you may need to build a bridge here and there in order to get there, you know. So is that a good idea to do? I don't know. It depends on how much you need to spend. If spending more money on the bridge here to get access to the powerhouse is cheaper than this type of arrangement or that type of arrangement, okay, this is a good choice. But if it is not, then that is like making more expensive choices and spending money for nothing. I also mentioned another day that this could be between different countries. Like, for example, this is a project between Romania and Yugoslavia, the old Yugoslavia. So in here, there is a powerhouse this side and a powerhouse that side. Depends on the cross-boundary relationship and many other things, that how much power this country will get and how much power the other one. If the share of water from, you know, this river coming to this point is equally from two countries, they may get equal powers between each other. But if more of this water is coming from, let's say, Romania, only a little bit from Yugoslavia, then of course Romania will say that more water comes from our land, so I want to get more power here, right? And they have to make agreements, and then this powerhouse may be bigger and this may be smaller, so they will get a small kilowatt hour, and that will get more kilowatt hours. Because in terms of head, they both may have the same head, but in terms of the flow, one will use a smaller flow and one will use more flow, so one side will get more power, the other side will get less power, but that's how they have agreed, you know. And they will not be able to do anything, any changes in the river to bring more water to one side and bring more sediment to the other side, because that will cause some more political and diplomatic problems between the two countries. And as you see, this is like another type of development. These notes that I have given you is simply to study these drawings very carefully, because they will give you a lot of idea that if you get into designing a project similar to this, it will help you a lot and gives you a lot of good idea what to select. This is the art part of the hydroelectric power plants. From a vertical elevation point of view, as you see in this case, the water is getting into the turbine and then through the draft tube getting out. Now, In low head water power plants, if you see, and we will see some more of these drawings, there are different orientation of the turbines and generator. That is, if you have enough head, this means that vertically you have good space, you can have these vertical shaft machines. But if the head is very low, like 5 meters or few meters, then in that case you can use other types of machineries that instead of working horizontally with a vertical shaft, they may have a horizontal shaft or an inclined shaft, depending on how much head is available, how much is the difference in the vertical elevation. So you can do it, because otherwise this may be too tall for a small elevation difference. So this, you need to know these things. And also, when you get to the sites where there is a small head or elevation difference, normally if, for example, this is a Kaplan turbine, you may not use that type of turbine, you may need to use a different type of turbines, because this one doesn't really work. Kaplan turbines are not actually good to put them in horizontal shaft and then run them vertically. They're mainly good if the shaft is vertical and running horizontal. Now, this other thing here above the turbine is the generator. So we will learn soon how to couple the generator and the turbines together. Although we were talking about these things, we have not done anything about the turbines yet. We will soon get into turbines where we will discuss different types of turbines. But regardless of the types of turbines, there is one important thing in turbines which is called the specific speed. This specific speed is not really the actual speed of the shaft. It is another speed that hydraulic engineers and mechanical engineers like to talk about it, because based on that they select a turbine. So based on flow, based on head, and based on the specific speed, you select a turbine with the best efficiency. But then using the specific speed, we will see in the next few days how we select a pump generator in order to be able to couple with the turbines so it runs smoothly. It's like not possible that the turbine is running with 1 revolution per minute and then you couple a generator with it with another speed, actual speed with different revolution per minute. Because once they are coupled, the two will run with the same revolution per minute. Now if you selected one of these with the wrong actual revolution per minute, then it means that either it's running slow or too fast, which is not good for that machine that you selected. But we will get into that when we come to in here. I just wanted to show you that one of the setup is with this vertical type of shaft setup, where you set the turbine here and the generator above that, and then in here this is the inside the powerhouse with some sort of crane and everything that you can move the machineries. Now when the flow gets here, this opening and that opening, that is around the turbine. This is called a spiral case. So this is especially designed for that particular turbine. So it flows around it, and from each of these openings, the water will get here, and when it comes down, those blades have special types of forms that will exert a pressure on them, and they will start running around. And when that is passed, then the water will get through the draft tube to the downstream side. Now, the head on this turbine is the difference between upstream water level and downstream water level. Okay? Why? Because this part is connected to the downstream and therefore it's pressurized. It is similar to that other thing that one day I mentioned to you about orifices. Remember that we draw something like this, and then the water gets out of this. This is called free orifice. But if we have another basin here, and by the way, for the free orifice, this is the head that we are using for the free. And then if we have water up to, let's say, this level, this will be submerged orifice or even pressurized. So the head for that one is this difference. Okay? So similarly here, when the water flows from whatever the water level is there through the turbines and up to the downstream water level, the head will be the difference between upstream and downstream level. And if there is any head losses here and there that is not included in the turbine efficiency, then you have to calculate that and subtract that from the gross head to get the net head, and that will be the head that is used in the power and energy calculation. So they look similar, but they are a little bit different. Now, the same Kaplan turbines with the downstream water level and upstream water level, and similarly here with the downstream water level and upstream water level. If you see, this is actually the water is coming from a deeper elevation, but when it gets to the turbine, it passes through this opening and also from around it. So this is like maybe they didn't have enough room vertically, therefore they designed the channel a little bit deeper so the water can go through it, although they are not increasing the head with this type of thing, but somehow they were able to set up the turbines. Otherwise, if you shift this a little bit up, then there is no room vertically for the turbines to set in this case. So that is the little difference that you see in these cases. These bars that you see, they are some types of rocks because they don't want big objects to go to the turbines, like maybe tree branches or some bigger objects. They should be stopped. But again, depending on the sediment or water quality of the river, if there is a lot of sediment, you have to do something about it. If there is just a small amount of sediment, then it may be okay. But normally in low head plants, if the head is only a few meters, let's say 5 meters or less than 10 meters, because the head is very small, these sediments will not be too big in the river because simply the river is maybe too big, the cross-section of the water area is big enough, the velocity flowing through the river is small, therefore only small fine particles as suspension load may be in the flow, which may not cause problem to the turbines. But bigger things will be stopped. So imagine if there is a sand particle in a high head hydropower plants where the head is 100 meters or 200 meters, and with that head, that particle comes with super velocity and it hits the turbine. That is a big force that will damage the turbine blade. But in here, if a particle of clay is within the flow, and then there is only a few meters of it, hits the blade of the turbine, that's not going to cause anything. So I mentioned one thing, suspended load, which I'm not sure if you are familiar with this. These are the things that civil engineers, hydraulic engineers, dealing with rivers, with sediment transport, they know, because in rivers there are 3 types of sediments. One is called suspended load, which means that the particles are sort of, jumping up and down in the flow. One is dissolved load, so the material is dissolved with water. And the third one is the bed load. The bed load, when the material is moving in the flow only at the bottom, and there are bigger particles, and if you are dealing with mountainous rivers, they could be big stones and rocks. So this is why before we develop hydropower, the energy of water is used in transporting those material, big stone, suspended sediment, and everything else. Plus, when they fall, when a water falls, what happens to the head? The head, they say, dissipates. That means it's gone. So if you don't use it, there is no more head. Where it is gone, it's probably changed to heat or something. It is not destroyed from the nature, but is changed from one form to another. This is why in hydraulics, if sometimes they have a lot of energy in the stream, they need to design energy dissipators. Energy dissipators are nothing but something like steps. So you have a stream where it drops this much. So instead of this, you might put something like, so this water comes and this, now when it gets here, this much energy is not available anymore. It's already dropped between here and there. It went this much and that much and so on. So if you have a steep channel, then what you do, you design little check dams in order to stop erosion of the land. So by creating those steps, you are dissipating energy, and this is why these types of structures and hydraulics called energy dissipators. Because sometimes we need energy, sometimes we don't need energy. For those streams, because the water is not always there, you cannot say that, well, let's go and put a turbine there and create energy. You can do that, but that will be only like 15 days in a year. So the rest of the time your turbines will be just sitting there doing nothing. So spending a lot of money will not be worth it. But that 10-15 days of flow, if you don't design these energy dissipators, will erode and scour the land and cause a big problem. So in the farmland areas, in the mountains, and the cities where it is located on hilly areas, this is how they are dealing with the extra energy of the streams to make sure that nothing is damaged. Some more pictures are shown to also show you these things in the plan view. So there is a turbine, but the flow getting to the turbine is channelized like this because you want to bring the flow in a smooth way to the turbines. If you don't do that, then when the water comes like a straight line, and then suddenly there are some changes here and there, what happens is that the flow gets very turbulent. When it gets very turbulent, you lose a lot of energy. Okay? So all these little things that engineers do in the projects, it is simply to gain the energy that otherwise it will be lost, so we can produce electricity. Okay? One of the things in hydraulics is that when you have an abrupt change, it's very difficult. Therefore, everything needs to be changed gradually. Okay? And if you don't know how to design this, maybe the best thing is to do a model test and then use different design in the model test and measure the head loss from upstream to the downstream and see which one gives you the minimum head loss. Then that will be a better way of doing this. Or if you are familiar with computational fluid dynamics, you can model this in those softwares and see which design really gives you the minimum head loss, so you can have more head for producing energy. So in here there is a rock. Soon we will see how we can calculate the head losses. But before going to that, if you see now we are dealing with turbines that are more or less with horizontal shaft, but they are not Copeland turbines anymore. They are called bulb turbines, less like these electric bulbs, because they have a shape that when water flows through, just like fish in the water, so it will have less resistance. See the ships, when they move in water, their shape is so that they cause less head loss. In another word, if the shape of a fish was rectangular, this fish would have had to spend a lot of energy to move, right? But now, because the shape is so smooth to the flow, then with just a little motion, they can move wherever they want. Similarly, for cars and airplanes and everything, that's why they design it similar to fishes, that when they flow, the faster they flow and the faster they move, then there is less drag force on them, and therefore they don't need to spend a lot of energy in order to travel from one point to another point. So in here, the turbine is not traveling anywhere. It is the water that is traveling. Okay? So relative to the water, the turbine is stationary, but if we consider that water is stationary, then the turbine is moving with a speed equal to the velocity of water. Okay, that's like relative velocity, which doesn't matter which way you think, it's both the same. But the thing is that in here, the shaft of the turbine is horizontal. Now the shaft is horizontal, but how do you connect this to the generator? In some cases, at the other side of the turbine, they built another room and they connect the generator with a horizontal shaft. But in some other cases, they use a gear, so the motion of this shaft is this changed with this gear to a vertical motion, and then they put the generator in an upper level. The generator will move with a vertical shaft. The turbine is moving with a horizontal shaft. The two is coupled with a gear. Most of you are mechanical engineers and you know gear better than me, how they work and how they are designed. But what happens in that case, some energy will be lost in the gear, right? So from this shaft to that shaft, you can also change the speed of this shaft with the other shaft, with designing your gear accordingly, that one moves faster, the other one slower, but that's your choice. And the thing is that you should do it in a way to lose less energy. Some more example. For example, I said this is the turbine. The shaft is going this way. Now in another space outside the flow, which is dry, there is a generator. So now both of these have horizontal shafts. This one is similarly a vertical shaft with the generator located above it. And as you see, this is a different design. It might be a smaller application, so they divide the flow in such a way that this may be sufficient. But in here, which is also there is a rack to stop, foreign material to get into the system. You look carefully in this picture from hydraulics point of view, the tailwater is here and the upstream water level is there. So the head is between that level and this level. Okay? If the water level is lower than that, then the water, let's say the water level is halfway here. What's going to happen? You will create an open channel type of flow here. That means that part of the turbine will not get water. This means that the turbine will not work properly. So in order to make sure that this does not happen, if that is the case, you should set the turbine lower so it is always submerged in water. Okay? So this is apart from very primitive type of turbines. The other turbines are mainly submerged in water. But if you are thinking of Pelton turbine where there is a lot of blades and a number of jets, in that one it is not submerged. It's just like a free jet hitting the blades. But that's different types of turbines and different design. And if you lose a meter or half a meter in that, it doesn't matter because the head is probably 200 meter, 100 meter, or it's so high that just a little bit head doesn't really matter. But even for that, you can design it so that when the water is hitting the turbine, it is hitting it at that elevation that it is not really too far from downstream water level, just like a few centimeters or maybe half a meter or something. There are even smaller low head plants that if you see on one hand water is flowing over it when there is a high water, a flood, and then when there is a lower water level, then the water will go through these sections and produce some electricity. This type of arrangement is sometimes used. It depends on where you have the site. It is always better to select a site where there is a curve, a bend, or a meandering. Why? Because if you cut a smaller channel just for the turbines flow, that means that this length from here to there is smaller than the length from here to there. What does causes when the length is long, we are talking about the same water level here and there. So in a shorter length, you go for the same difference. That means that you can use more head. In the other longer, if you make this longer and longer and longer, that means that, you know, for the same water to flow from here to there, you need more head. But if you cut it short, you need less head. Some part of the head is then can be used for producing energy. So besides whatever head that they get from here to there, in doing this, they can add some more energy in terms of head energy to the system so they can produce a little bit more electric power. And this is mainly if you have this sort of option. But then if you do that, you have different options. You can build a powerhouse here, you can build a powerhouse there, or you can build a powerhouse here. It all depends on the situation that you need to do some analysis in which case you get more power, which one will be more feasible economically, and so on. So it is not like this one is better than the other one or the other one is better than the other one. You can select any of them, but then you need to do some analysis to find out which one is technically better and which one is economically better and even which one is environmentally better. We have to find those things and then select those things. Sometimes low head power plants are also built underground. Excuse me. So if you have this opportunity to build underground, it may have a number of advantages. For example, instead of building this in the river like we have the weir and then the powerhouse, you can put it underground so there is more room for the overflow, right? So this is not really blocking the river cross section by any means. It's just on one side, and even it could be under the same river because you are taking the space underground, under the bed of the river, you know. But you have to be careful about the material getting it because if it is really under the river, and if the bed is the same as the intake, then a lot of sediment will get into that river. But you can take the inlet at an upper elevation, because that is okay. It doesn't matter from where the water gets into the system, because the head is between this level and that level. So you are not really changing the head by putting your inlet lower or higher. But because this is an underground development, it is better to put the intake to the system at a higher elevation than the bed of the river, so sediments will not get into it. But then you can have a shaft like this going vertically, or then horizontally, or you can have it inclined. It all depends how important is this project, how big is this project, how big are the turbines. If it is really like a small scheme, you can have like an inclined shaft, no problem. But when it gets bigger and bigger and bigger, then you need to make it smooth for the flow, that you don't lose a lot of energy. And then you can put the rest of the thing. There is also a surge tank here. This is needed if this tunnel taking the flow back to the river is long. Sometimes you know what they do? They don't bring the water from here back to there to the river, because if they do that, the head will be small. But if they built a tunnel and then downstream 500 meters, let's say, it joins the river, at that point the river has a much lower energy elevation. Therefore, the energy in this plant is used from here to wherever this tunnel is joining the water level. So this tunnel, because it is built below, it will go all the way to the river with more or less the same slope or a small slope, but it will be most of the time submerged because of the influence of the downstream water level. And therefore, in order not to get damaged, then they built a small surge tank here. And because the surge tank is closed, it may be working like these water supply pressure release type of devices, where they have air. So if above the water level there is air, so whenever the turbine is opened and closed, there will be some waves, just like the surge tank at the upstream side, and then the air inside will get compressed or not compressed, and that way this will absorb the pressure wave, and the tunnel downstream will not get damaged. Otherwise, you need to design a very strong tunnel. That means that the lining should be very expensive, whether it may be steel or very thick reinforced concrete, which may be very expensive. But with putting a surge tank at the downstream side, you can save some money. This is another similar sort of arrangement. So, as you see, these are all the arts of hydropower developments, which whenever you have a project to design something like this, it would be good to consider all these different options and see which one will give you more energy, more feasible, and more economical. In here we come to some calculations, and a part of the system. This is a rack. We need to put something in order to stop bigger objects to get into this canal. It could be a canal, it could be just a penstock, whatever. This is like an intake, so we need to make sure that foreign materials will not get into this. This is mainly for big objects. And there is one formula which is called Kirchner formula. I don't know how well you see it. Do you have your copies with you or your computers? Then you can see the formula. This formula is very much used in Europe, okay? Not much used in the United States. I don't know why, but the Europeans use this very much. And in this note you see it because this note is written by Professor Moshoni, the person that I showed you the other day with big books, and he is an European guy, so this is why you see this in his book. But nowadays they are using it, and the reason I wanted you to use this is really a good formula. And if you see this figure here, depending on what types of rods you are using, then you select a coefficient for that and then carry out a calculation using this. Tomorrow you will have two exercises. One will be an open channel type of calculation, and the next one will be a head loss calculation using this formula, okay? Which then you will return the assignment from today and tomorrow on Monday. This, let me have a closer look. Like any other local head loss calculations, this is a function of v square over 2g, or velocity head. Anytime that you are calculating a local head loss, something times v square over 2g. Now you can put all these other things into one formula and call it k, then it will be k times v square over 2g, which is similar to a bend loss, an expansion loss, a contraction loss, whatever you have, they're all k times v square over 2g. But in a bend or contraction or expansion, those coefficients are given by just one number. But in here, because you are probably using one of these different shapes in order to design the rack, then whichever shapes of the rods you are using, then you can select the right coefficient for it and use it in that formula. So with one k value, in this case it is not possible, but in general it is more or less the same thing as every other local head loss calculations. Is this clear to you? These types of things are designed either by civil structural engineers or mechanical engineers. They are mainly a steel design type of things, you know, from a structural point of view, because you have to design it for that as well. What is the hydrostatic head? What is the hydrodynamic head? Remember that first couple of days we were dealing with some formulas that you find the forces by flow or by static head. you can use those formulas here to calculate the forces on the rock, and then when you have the hydrostatic force plus some other loads from dead loads, the weight of itself and etc., then you can design it. And designing these from a structural point of view is nothing but you need to determine the section modulus. And once you have that, you go to some steel design handbooks and select the right cross sections, and then that's it. But if you get something that is very different from your hydraulic analysis, then you have to do your hydraulic analysis for head loss calculations again. Okay? So this also tells you that what types of shapes to select will give you the minimum head loss. All these shapes will have a different types of impact in terms of head loss. So sometimes you consider that, but then when you go to the structural design, you may think that, from a structural point of view, then it becomes too big, and therefore instead of that one, I may use this one because the moment of inertia in that one is bigger, so it gives me a better strength, and therefore, but then hydraulic engineers will not really argue with that because the thing has to be structurally designed as well, so it should resist the loads and everything as well. So these are the type of things that we do, and at the end we will select the one that it works from both or many points of view, and then that will be our final design. But these things, whatever you design, I think it will be mainly made of stainless steel, because we don't want to use mild steel or other types of steel, otherwise it will get corroded easily. So we don't want to use something that in a few months when we go there it looks like an old piece of metal, and that is not good. But when we use a stainless steel, they are very expensive. So you may think of something else like fiberglass or something, but then if you use fiberglass, you may not be able to get very small sections. So I don't know. These are the type of things that engineers need to think about it all the time. Different types of material, different types of designs, and then we deal these things from an economical point of view and make decisions on what to use and how to use these things. I really didn't go through the formula because it's just mathematical equations. All the parameters are written there. So tomorrow when we do an example, I will give you all the data, and you just use the formula to calculate the head loss. By doing this, I want to get two things. One, a little bit familiarity with the equation, and also a little bit of idea to see how much head loss these rocks can cause. Okay? Because that is always important to us when we are dealing with hydropower developments. We want to not waste any energy, but we can't do that. We need to, use some energy for all these different things in order to make sure that other things does not happen. If we don't put this, we don't lose any energy, but then we are in the danger of some big material will go to the turbine and damage the turbine. So there is a good reason for this to include it into the system. Till what time are we here today? If we are going to come again, then we make a break here because I see some of you is like feeling sleepy. And then I think our program is still about 2 o'clock. Is that right? So we make a break here and then we come back in 15 minutes. Is that enough or you want more? Huh?
Lunchtime.
Lunchtime? Money y over d's. Because y d stays the same. It is the big depth, the total depth, and y changes. So maybe the more lines you do, the more accurate it will become. And similarly, for every y, you calculate A, and you also calculate the width perimeter P. So you get a small p over the big P, which is all around, right? So you can create a table, and then if you want, you can also plot this in Excel, and Excel can also generate equations for you. Okay? So next time when you need, you don't have anything else, you want to calculate the flow for a given y, and then you know the diameter, then you know this y over d. When you know y over d, you know, from this table, wherever this is y over d, then you know A over A and a small width perimeter over the total width perimeter. Okay? So for this partial, every time you know the other ones, then you can calculate those ratios, and when you are done, you can calculate a small a or a small p, because here you get A over A and P over big P. At the end, you can determine A and P, right? So the ratio of A over P is what? Is equal to the hydraulic radius. So in this equation, you have the hydraulic radius, and the A that you are using should be the small a, right? The roughness and the slope, then you can calculate the flow for every water level that you need to do. Is this clear to everybody? Because there is no such universal formula that for tunnels you can use. There are formulas, I'm not saying, but that will be for a specific shape, because different people will design different shaped tunnels, you know. Now, how do you calculate the flow partially going through the tunnel? If you have those equations for width perimeter or the area for partially filled tunnel, no problem, you can use that. But if you don't have, this is another way of doing it.
Is it this center is the reference of our geometrical circle, yes? What about this small a? Where is the reference? From where is this?
No. There's no reference. You don't need a reference. What you need is, you need to measure, sorry, let me get another pen. The only thing we need is, from this level, how far we go This is Y. So if this tunnel is filled with water at this level, this is a small a. Is it clear? Yeah, you need to calculate either. I asked you to calculate this area by AutoCAD or by some other means, depending on what shapes you have. You can use geometrical formulas to calculate that, because in that case then you can do different things, like for half of the above part, this is half of the circle. Now how you calculate that, that's a different story. There are formulas that you can do that. I can give you all those formulas one day, but for this part it is like not circle but these other shapes. So you need to know some geometry to do that. Or if you don't know anything about geometry, use AutoCAD, select a line here, and then the AutoCAD select all these boundaries, will give you the area. Then you go to the next line. This will be your next Y. So the area is now larger. A small a. Big A is constant, the big area. So every time we are making this, only this changes, only that changes, only that changes. These others are constant because the big D is constant, the big A is constant, and the big width perimeter is constant. You can also have another one with B over B. Now this is the bottom width. These other B's are inside. So the maximum would be in here in the middle, which is equal to the diameter of the tunnel. So the smaller layers you do, more accurate your table will be, because later if you have a depth which is between two lines, if the two lines are close, then you need to do some interpolations and other things in order to get those ratios. The whole idea is to calculate a small a and a small p, and if you don't want to do that, you don't want to prepare this table, that's up to you. Then every time you have those different depths, you can calculate it every time. But what I'm saying is that if you prepare this and create even some equation in Excel, keep it every time you need it, then it will be ready. You just specify Y, then it will give you A, small p, and the other width, and that will make it a lot easier for you. That was the point. Did I answer your question? But there is no reference or anything to deal with this. I wanted to mention a couple of other things. Maybe you have a river that you divert the flow through a canal or some other branch, but this branch will never join this river again. Okay? Then you have to be careful about the environmental flow. That means that you cannot take all the water from this branch to produce electricity. What happens to the flow to this branch? So you need to leave whatever amount is needed. Maybe a small amount just for environmental purposes, or maybe as much as people need this for irrigation or other use. Whatever the requirements may be here, you need to let that flow go downstream, and then you want to develop a hydropower on this branch, then the remaining is something that you can use it for producing electricity. If you develop this somewhere upstream, then you probably do not need to consider these things and you can use more water. But sometimes, somehow, it may be a case that this is what you need to do. Therefore, you have to be careful about leaving the amount of water for another use, for other people, for other area, even for environment, for fishes, for trees and flowers and bushes and everything else, because you cannot take everything just for one use and then destroy every other thing. So we did mention about flooding or high water or maximum flow. In low head, both flow and the head fluctuates a lot compared to high head. So in high head, if you have 200-300 meters, and if there is a 10 meter of fluctuation, it's not really a big fluctuation. But if you have a 10 meter of head, and there is a 5 meter of fluctuation, that's a big one, you know. So what this means, it means that you don't have the flow and the head all the time on the turbines. So you have to be careful about the type of turbines that you are selecting, because turbines, if they don't get their design flow and head, then they may not function efficiently. So what you can do is to select such a turbine that every time there is a different flow and different head, they can still do a good job, which means that there are the type of turbines that inside the turbines a number of things changes with the flow, and therefore it makes sure that every time you get a good efficiency. So this is more important in low head plants. If you remember from the first overview, in the turbines for high head, we had Pelton types of turbines. Okay? There was nothing really changing on Pelton turbines. There was even a gap, like an air gap between the blades and the flow getting out of the jet. So this jet is hitting that blade, and then nothing changes in the turbine. This velocity coming out of the jet may vary a little bit because there is little variations in the head and not much. So Pelton turbines are more or less like constant type of turbines. You don't have to change anything. Kaplan turbines for the low head is also sort of not really moving parts. It is mainly the Francis type of turbines that they have some sort of mechanism that based on what type of flow they get, they change their openings in order to make sure that they have good efficiency for different flows and different heads. So this is a good thing, because engineers who developed these equipments, they were aware of these changes, and this is why we have these options that with different applications, we select the right turbines to use. Otherwise, if you select a constant type of turbines with a variable head and flow, that may not be a good choice. But if you select the one that with the changes in flow and head, the turbine also regulate itself, then that will be the best application for that case. I don't want to go to these other parts where there are some equations and analysis, because you will do that tomorrow, and I want you to be fresh and good. And in this note here, from some sort of head calculation, then they go to generators. But I don't want to follow that, because I wanted to give you some information about turbines for low head, and then we can come back to this to see how the generators are coupled with turbines, and we are talking about low head plants. So then for high head plants there will be different turbines, and you will have different sort of information, different cases, different situation to deal with. Now we have something like less than half an hour. I like to ask if anybody has any question so far from the beginning till now, and also I want to know if every group has given me their project title and objectives, and if they have not, and if they are here, please come and talk with me. But after the half an hour, because I don't want that everybody else is here and may have some questions, and we can talk about your projects later after 2:30. So, any questions so far? Have you really got some idea about hydropower and some hydraulic calculations and everything in this past week that we had? We started last week on Saturday, right? So this is a week plus 1 day today, 8 days. And I hope that you have learned something, and by now you are probably familiar with my accent, which is a very bad accent, by the way. Many people don't like it, but if you understand me, that's a good thing to do. I know this type of courses, you know, you need a lot more time, but unfortunately this is only for a month. So we are gone 25%, and then next week by this time we will be done 50%. So you see, next week it is like we are going to the top of the mountain and going slowly down. So this is why I'm really asking you to pay more attention on your projects. And so, any question on the type of material that we discussed, about some simple and basic hydraulics, those basic laws? Because if you don't have question, then I'm going to ask you some questions. Is that okay? Is continuity principle clear to everyone? Yeah? If it is clear, I like that somebody tell me on what is continuity based. Any idea? Continuity is based on what? On what? On the law of conservation of? Okay, that is good, that's right. So what does it mean? What is law of conservation of mass? I'm really sorry, I cannot hear. I have very bad ears. So
cannot create or destroy.
Okay.
And the volume of initial volume of the
So you cannot create or destroy mass, right? But you can change it from one form to another, and then this continuity law is based on that. And when we talk about hydraulics, fluid mechanics, we are talking about flow. So this means that if we have a constant flow here, it passes through a number of different channels and pipes and everything. So if we consider or measure the flow in another point, it should be the same, provided that there is no storage in between. Okay? So you cannot say that I measured the flow here, it was 10 cubic meter per second. When I measured it 100 meters further, it was 8 cubic meter per second. So what happened with the other 2 cubic meter per second? I don't know. Maybe there's a leak, maybe the flow is going somewhere, or maybe this is a big tank that every 2 cubic meter per second is stored there. So if there is no storage and everything is flowing everything else, the same amount of water that passes this section should be the same amount at the other section. So using this principle, then what we do, flow is the cross-sectional area times velocity. So if this is in square units and this is in length unit per time, when you multiply the two, you get discharge, cubic unit per time. So that gives us a good thing, and if we know the area and the flow here, then we can do something to get information about some other section if we don't have that information. So continuity will be used in many cases to help us determine some other parameters. So what is the energy equation or Bernoulli equation is based on? On which principle? On energy principle. And what is that? Same thing, we cannot create and we cannot destroy energy. So we just change energy from one form to another form. The most important thing that you need to remember in fluid mechanics and hydraulics, we are dealing with energy in terms of a vertical elevation. This is why we always measure energy in meter, in feet, in centimeter, and whatever length dimension, and that is a vertical measured dimension. And why we do that? Because we want to make it simple to make our work simple. Otherwise it will be too complicated if we put like the elevation differences in meter and then the flow energy is in calorie and the the velocity head is in kilowatt hour, then I don't know what to deal with this. So if we put everything in meter, then one is the kinetic head, which is in meter. The other one is the flow depth, which is in meter. The third one is the geodetic vertical distance from a datum, that's also in meter. So it makes easy. So if we consider a channel at two different sections, all this vertical height must be the same as the other vertical height, but on the other side there will be some losses. Why? Because flow, like we walk or run, water also needs some energy to move from one point to another point. So when we say head loss, friction loss, or whatever loss, it means that the energy the water used to move from one point to another point. and that energy is in meter. We measure it. So this is the Bernoulli equation, or the energy equation, which is a very useful one. You can combine the continuity with energy equation and create other equations. Then we talked about momentum principle. That one is based on the second law of Newton, when we say F is equal to ma. So instead of mass, we use rho g, and instead of a, which is the acceleration, we use the second velocity minus the first velocity divided by time. So you get something in meter per time square, or length per time square. So using that, then we get an equation that we can use for forces due to hydrodynamic. This is not hydrostatic force. This is the hydrodynamic force. So that way, if you have a body under a flowing water, you have a hydrostatic force on that body, and plus you have a hydrodynamic force on that body. So if you want to do something with it, like do a structural design, you need to determine all these forces. And if you want to use these hydrodynamic or static forces for other purposes, you can similarly use and develop other equations. So everything that we are doing in fluid mechanics and hydraulics, they are not out of these laws. No way. Whether sometimes you may use or may see this principle in one dimension, in one direction. Sometimes you may see it in two-dimensional case. Sometimes you may see it in three-dimensional case. Okay? So, but then it is all the same. Like remember, for the forces, we had an x component, we had a y component. You can similarly have a z component. Similarly for velocity and for pressure and everything. All these quantities that have a vector quantity, they also have directions, and therefore you can use three-dimensional or two-dimensional or one-dimensional. It is up to you. In the hydraulic modeling, if you are dealing with a river, they use the full hydrodynamic equations in one dimension. But if the rivers are really wide, then they can also use a two-dimensional model. But when you use a two-dimensional model, you have to specify, is this like in the longitudinal direction of the river one dimension, and which one is the next dimension? Is it in the depth or in the sidewise? You know what I mean? Because if the river is shallow and very wide, they want to use the horizontal direction. They don't care about the depth. But if the river is really deep, then they want to use this x direction and the vertical direction, because in every layer there may be a different velocity, and therefore a different shear stress, a different sort of pressure and everything. Similarly, if the river is too wide, then in this two sides of the channel there may be different velocities. Therefore, if they just use one single one-dimensional model, the velocity distribution will not be what they get from that model. Use three-dimensional models, because In groundwater, you don't know the water is flowing this way, that way, the other way, up and down, how it is working. But it works in all directions. So when they model groundwater, they use those equations of groundwater to model this. Those equations for groundwater, they are called Darcy equations. Not the Darcy-Weisbach that we saw for pipes, but only Darcy is the same Darcy who sort of evaluated those flows in groundwater as well. So similarly in hydrology, when people calculate water on land surface, they can use a two-dimensional model, because if the hydrology calculation is based on hydraulic principles, then they normally use a two-dimensional model in order to calculate the flow. This is called surface flow, and sometimes it is very important to do this. But when you do these types of things nowadays, it is all software models that are used, because by hand they are very complicated. So when you go to two-dimensional, it is not hand calculation anymore. You need to deal with differential equations, partial differential equations, and then you have to use a numerical scheme to solve it. Then you need to create a computer program for it, and then you work with it to see if everything is okay. So now you are familiar with flow through pipes, flow in open channels, and basic classification of hydropower developments, a little bit more on low head plants, and you saw briefly power tunnel and surge tank and penstock, and slowly we will get into a little bit more depths and details. So please work out this in the afternoon. Tomorrow you will have a chance to ask me. I did not put the Manning's roughness coefficient for concrete and PVC. I also did not put any local head loss coefficients, those K values, K times V square over 2G. And remember the energy grade line and the hydraulic grade line that we discussed the other day? So the whole question in here is, how much is this big H going to be in order for that flow, which is about 0.03 cubic meter per second, to flow through these pipes. So you need to calculate friction losses for the three pipes and all those local head losses, and then sum them up to see how much is this. But for the energy grade line and hydraulic grade line, you need to draw it approximately. You know that the difference between hydraulic grade line and energy grade line is that the energy grade line is below the hydraulic grade line is below the energy grade line by an amount V square over 2G. So this is solved. You just do the calculation, right? But I want you to do this simple example, because if you do this, you should be able to do anything. If somebody asks you to calculate the flow and they give you the H, that will be a little bit more complicated, but you can do it, you know. What you can do, if you are really interested, once you calculate this H, then assume that you don't know the flow. see how you can calculate to get the flow. If your calculation gives you a flow 0.03, then your head calculation was correct and your other calculation is correct as well. But in the reverse way, if your discharge calculation is not 0.03, then you may have either done some mistakes in calculating the discharge, or you may have even done some mistakes in the calculation of the head to begin with. So you can check with yourself, and also you can learn another way of dealing with this problem. And if you do this, then whatever problem of this type is given to you, or pipelines, you should be able to do it without any problem. You can also use Chazy equation, or you can use Manning's equation, or you can use Darcy-Weisbach equation. I leave it to you. So thank you very much, and see you tomorrow.